My name is Chris Dent from Durham University. I'm chairing this morning. Two announcements. The usual one, please turn off mobile phones. And we don't just mean please put them on silent, we mean turn them off because the signals interfere with the AV equipment in the room. Second thing is, you may have seen at the registration desk flyers for a special issue of the Journal of Risk and Reliability, which several people here are guest editors. Special issue on risk and reliability modelling of energy systems, and hope this will fulfil two purposes of providing a summary of where the state of the art is, and also continuing bringing together the mathematical science and power systems engineering community, both, and the combination of both of those is vital in this area. So if you're interested in this field and would like to think about submitting a paper to this, then please take one of these flyers. Now onto the main business. For those of you who were here yesterday, I think Mark O'Malley from University College Dublin needs no introduction. But Mark has been he's a major figure in wind integration studies. He's advised wind integration studies worldwide, and he's going to talk to us today about the needs for such wind integration studies. Okay.
Can you hear me? I reckon I should put a target on my back. I suppose after yesterday I have to be a bit careful. So I bought Yanis a beer last night. Daniel, where were you? Daniel, if you were there, I would have bought you a beer. But you weren't there. Okay, just very first thing, just to say a little bit about the research group that I run in Ireland. It's very much, in fact, I like this. This is a good, there's a laser pointer, but this will help me defend myself against Yanis if he comes up. So it's a very much an industry-supported research group. Its entire funding base was originally industry. So I come from very much an applied industry type background. And I mean, it's chaired by the Irish Energy Regulator. The great thing about a country like Ireland is a small country, you have access to everybody. And these are the people look, there you go, Yanis, look. We collaborate. I have a policy in life that says I should only ever collaborate with 3 groups, because one in the UK, one in Europe, and one in the USA. And it's very simple. It's because collaborating with people takes time. So that's just the research group, very briefly. I decided to start with the acknowledgements first. And I want to thank them, because what they did is they covered a lot of the introductory material yesterday, which I think was very useful. I want to thank Chris in particular and the Isaac Newton Institute. So they're all the people that I work with, etc. So an awful lot of the work I'll talk about is related to them. This was a very difficult talk to put together, because it's not I'm not here giving research results. I'm not here giving a sort of a class. It's somewhere in between. So it's a very difficult format, isn't it? Well, I found it difficult to do. So so hopefully the slides will do some good. I've got a lot of slides. I decided that I'd cover a lot of ground at a fairly high level, and just to spark your interest more than anything else. But the contents and key messages, and I had the advantage that I did these slides at the back of the room yesterday, so they're sort of up to date as opposed to I didn't do them last week. So in many ways, I think I might have captured some of the discussion points that were mentioned yesterday. So hopefully they're just-in-time slides. And that's appropriate to wind, because wind changes, and you have to act just in time. So I'll start with a bit of a tutorial about wind and power systems. And then, I mean, what are wind integration studies? I mean, we talk about them, but I'll tell you what they are and why are they important, okay? So I think it's a very important, from my own background, what I always find is that, because I work a lot with industry are the customer, you have to understand what they want, okay? Some academics think that research is just to be done for their own good, which is fine, but in applied research, it really has to do with the customer, what they want. So I'll tell you why they're important. And some interesting research questions, okay? I'll cover some, there's many more, but I'll cover a few. What are relevant? I mean, it's all well and good doing maths, but it may not be relevant. And I'm all in favor of doing irrelevant mathematics, it's fine, But if you're going to apply it to energy systems and you're going to get the interest of industry and get data from them, it better be relevant to some extent. So, I mean, this is easy to cover. Wind, I mean, we're not going to cover climate change and all that good stuff. But, you know, the world, for security supply reasons and for the environment, there's an awful lot of wind power being proposed, been built. And if you look at the wind speeds offshore and onshore, the blue is high wind speeds. And you can see that basically the UK and Ireland, particularly Scotland and Ireland, are where the major wind resource is in Western Europe in terms of its quality, okay? Germany has an awful lot of wind, but a very poor wind resource, okay? So that's the context. The UK and Ireland in particular have a huge wind resource, and it's starting to grow fairly dramatically. In Ireland's case, this data is a little bit out of date. It's up to 2008. I should have 2009 data there, I just haven't got it yet. But you can see that the growth is exponential, okay? At the moment, right now, I think we have 1.3 gigawatts of installed wind in the system. Now, to put that in context, there's another slide later on that puts that in context to show you how large that is. Our system's incredibly small. We're 1/15 the size of the UK system, yet we have half the amount of wind. So pro rata, we're 7 times bigger in terms of penetration level. But there's a slide later on that does this quite well. So that's wind, and just for political, this is the Republic of Ireland. We all know the difference, don't we?
When you use megawatts, is that a maximum capacity or a maximum
Yeah.
capacity?
This is installed nameplate capacity. If the wind was roaring across the whole of Ireland, max power, well, actually, sorry, if the wind was roaring across the whole of Ireland at max strength, they might all turn off because they have the problem that too much wind's a bad time. This is the maximum installed capacity. That's the absolute maximum that they could do, okay? And sorry, if anyone wants to ask any questions, I'm open to questions during the slides, no problems at all. So just some very simple characteristics of wind. This is Irish wind data. It's given for every month, and every hour is average. So, you know, this is at noon each day, we took all the data for every month and added it all together and just give a sort of an average profile. So it's showing two things. It's showing the seasonal pattern. I mean, summer to winter, huge difference, okay? Basically in the summer, not so windy, in the winter, very windy. And it also shows a diurnal pattern during the day. Essentially, during the middle of the day, it tends to be windier than at night, okay? So that's the first thing. On a macro level, the wind has seasonal characteristics. It also has daily characteristics. But if you're to look at it, just in case you get sort of think that it's reasonably regular, just take 5 or 6 days in sequence, okay? Because this previous thing is an average over the month of May, for example. This is in sequence. They're 5 days in a row, and you can see every day is effectively different, okay? So it's variable. And also, we can't forecast it perfectly, and this is just a very simple graph that shows you, this is average wind, and this is the wind forecast. So system operators, when they're trying to operate the system, they have this resource that's variable over season, over the day. Every day is different, and they can't predict it ideally.
The forecast horizon.
He's older and wiser than you are, so you ask your question first.
What's this day ahead forecast?
I think in fact what this is that it's a day ahead forecast, but it's rolled over every 6 hours. So we do 6 hours and then we chop it off. So what you're seeing actually is the operational forecast in which the power system operator is operating on. Because you're right, you know, if you do day ahead, it gets, I mean, the error out here, if you were to forecast it here, would obviously be much bigger than that. So I think what it is, as far as I remember, is it's a 6 hour rolling forecast, and then we take each 6 hours, roll it ahead, and the data that's shown there is the 6 hours, the next 6 hours. Okay.
That's an average for the whole of the life.
No, this is actually just over the same days as I showed there previously, 6th to 10th of May.
No, sorry, geographically, do you have a single forecast for the whole region?
Yes. Yeah, the system operator has 2 forecasts. One is based on numerical weather prediction, and one is based on statistics. And one is sort of, I think it's 12 hours ahead, and the other one is 36 hours ahead. And they have some heuristic algorithm that they've learned over experience. There's a certain weighted combination of those that's the best one to use. It turns out that their own internal code that they wrote in an Excel spreadsheet is better than any the manufacturers have supplied to them.
Yes, but when you looked at the graph of where the wind speeds were, you've got much higher wind speeds, for example, in Northern Ireland.
Yes.
Southern or southeast of Ireland.
Yeah.
Are you using a single figure single forecast?
At the moment, we're using a single figure, but you raise an interesting point. As more and more wind comes onto it, we'll actually use regional forecasts for operational reasons. And actually, I have more slides about that, but they're not in this slide deck. But as we get more and more wind, you'll actually want regional forecasts. At the moment, we don't, but we will. Okay, so a little bit of a tutorial. Yanis did his little fella pulling a big rock up a hill type of thing. This is my analogy, and Daniel's was the beer for the reactive power. So this is my analogy for frequency control, which is it's a tank of water. Generation is water going in, and load is water coming out. And the level of water is analogous to the system frequency. So if I put too much water in, the frequency goes up. If I take too much, if I don't put enough water in, the frequency goes down. Okay, and that's just an analogy. And this here is to indicate that I must maintain the water level in perfect balance almost instantaneously. Not quite. Okay, there is some error. You're allowed to let the frequency drift a bit, but not a lot. Okay, so that's my analogy for it. And Yanis covered it very well yesterday. If you don't maintain that balance, the Italian blackout's a classic case of it. It was essentially a frequency problem. I mean, it was the transmission lines, the cascade effect. Eventually, they ended up with a frequency or a generation deficit. The frequency plummeted, and they lost the system. So the real question is this is the sort of the back of the Sunday Times type of argument, which is wind is variable. I can't predict it. So in order to maintain supply and demand balance, it's very difficult. Wind is bad for the system. That's the sort of a classic argument that goes on. Isn't that correct? That's what everybody hears? Yeah? Well, I'll go through a few pieces of research that relate to that issue, okay? So that's the first part of the tutorial. The next part is, who was up here yesterday who said all singing, all dancing transmission or networks? Did someone say that? Who was that? Was that you, Yanis? So Dana said all singing, all dancing, smart grids. There you go. That's Daniel, that's me, and this is Yanis. I'll email it to you, Yanis, you can have it. But on a more serious note, transmission. I was at a meeting in the Department of Energy in the US in Washington, D.C., which is here, about 2 years ago when the DOE put out their 20% study. I do an awful lot of work in the USA. I'm basically almost co-located sometimes between Ireland and the USA. But at a DOE meeting in Washington, D.C., there was a bunch of, there was the wind industry, there was some academics and whatever, and it was a sort of a talking shop to say what are the key issues about wind. And without going into too much detail, I said it and some other people said it, but it came out very clear. The single biggest thing that the wind industry faces is building transmission. There are some other very interesting problems that Daniel and Yanis and me will want to solve, but at the end of the day, the single biggest problem is building transmission. The Irish Energy Minister, when we did a grid study called the All-Ireland Grid Study, I met the Irish Energy Minister 2 days before it was released, and he wanted to ask some questions. I told him, look, all those questions we can solve all those. Can you convince the Irish people to allow you to build 2,000 kilometres of high voltage transmission? Because if you can't have what you want. So wind requires this stuff. This is a map of the USA to show you. I mean, it's color coded, but basically all the wind, the best wind resource in the United States is in the middle of the United States. If you've ever been to the middle of the United States, there's not a lot there. North Dakota, South Dakota, a place like that. Wyoming, we don't have a lot of people. The people live in the coasts mainly, or in the lakes area, or over in the East Coast. Therefore, you have to build large amounts of transmission. Okay, so I use that to sort of, it's not just an Irish problem. So wind needs transmission. It needs to go large distances in some places, smaller. This is a picture from Ireland, pylons out, just as in. The public are the biggest problem. They want green energy, but they don't want us to build transmission. Now, there's another slide later on. In my view, in this area, the most at the sort of the pyramid of this area, academically, are electrical engineers, obviously, no doubt about that. Then there's economists, and then there's mathematicians. But there's another group of academic disciplines that's in there somewhere, and I'll leave you with that thought. And there's a prize for anyone who can answer what it is. Capacity credit. This was mentioned yesterday as well. It's very important from the point of view of transmission and other issues. What this shows you from a reliability point of view is how much wind contributes towards meeting the peak demand. It's a very simple description of it. But basically, if I install 1 megawatt of wind, I essentially can meet 0.4 megawatts of extra load reliably across the year. But as I put more and more wind on it, the amount that I can meet reliably, so if I have 6 gigawatts of wind, yes, in absolute terms I can meet more load reliably, but in relative terms I can't. And the reason it declines like this is because wind is not independent of one another. In other words, if wind farm A and wind farm B are close together, you'll find that if wind farm A, the wind is blowing, it's likely that wind farm B, the wind is blowing as well. So they're not independent of each other, and hence this characteristic from a reliability point of view. But what it does is, from the point of view of building transmission, if you look at the fact that the capacity factors are low, the capacity credit is low, your classic case, traditionally, if you built a 1 gigawatt nuclear plant, you'd build enough transmission to take the 1 gigawatt 24/7, 365 days a year. That's effectively what you would do. But with wind, you'd have to say to yourself, well, you know, on average, it's sort of 30% blowing, and from a reliability point of view, it's not contributing a lot. So you wonder to yourself, should you construct a transmission system in the same way you did before? And it brings up some of the issues that were discussed yesterday. Similar question.
I'm not as wise as Janice,
Yeah.
so that would mean if I just build one single wind turbine, that's the most reliable output, because that somewhat contradicts the intuition.
Yeah, but no, in relative terms it is. In absolute terms it's not. This is percent. The capacity credit in absolute terms is rising, but the incremental change is not as big. And this is the diagram that from an economic point of view that kills wind. You know, it means that at 6 gigawatts of wind, it effectively says that you can replace 500 or 600 megawatts of thermal plant. That's all. So from a capital investment point of view, it's the killer. Yep.
And this reflects the geographical scale of Ireland.
Yeah. This characteristic here has to do with the fact that all the wind is correlated. In a bigger footprint, it might go down less. In a smaller footprint, it might go down more. It depends on the weather characteristics, etc. Also, be very careful. This varies by the year. This characteristic can have a plus or minus 10% deviation from year to year. So if you do your capacity credit calculation on 1 year's worth of data, you could get it badly wrong. This is just one that I can't remember where this one came from, but we just published a paper in the IEEE Transactions that shows how many years worth of data and how much data you need to get a robust answer to this question.
It's not just the correlation with wind farm, is it? It's the inherent variability of wind in relation to the variability in the conventional capacity. And if even your independent wind farms are all operating independent of each other, you still see a similar phenomenon.
No, this diagram is completely, I can assure you, this diagram is totally and absolutely dependent on the if I had wind farms that were totally independent of each other, this diagram would look a straight line.
We have a discussion about that.
Yeah, no problems. I'll ask Janice to come and help me. Okay, so open questions, increased wind energy. I showed this, you know what's underneath this thing of pile, yeah? There's a metal spike. And actually on the news last night it was saying that people in Cambridge jump off the bridges. What do they call it? Some activity called, there was a name for it. But apparently some lady here last year jumped off a bridge and there was an old punting pole and she impaled herself on it. Yeah? No? It was on the news this morning. Anyway, my analogy here is that this kid is taking a bit of a risk because he's no idea what's under the leaves. So the open questions, and this is sort of an analogy to say, well, we're going into the unknown. So the question is how will we operate it reliably? And there's things like frequency control, voltage control. I won't talk much about voltage control. Some people talked about it yesterday. And I think the analogy of the beer, I think we'd have to spend a long time going through the tutorial before we get to the meat of that. How we plan the transmission system, the generation system on the basis of the characteristics of wind, will it be different? And the disciplines are electrical engineering, economics, question mark.
Social science.
Hey, who wins the prize? Yeah, there's no doubt about it, the social sciences are incredibly important in this. Because if people want, for all sorts of reasons, will society accept the transmission? And also then on this smart grid thing, how they'll behave. So it's probably it's one of the most important disciplines of all. How human beings will behave. I owe you a beer. And the only way we can do this is with modelling and simulation, because we don't have systems with large amounts of wind. So there's a lot of modelling and simulation, there's a lot of stochastic optimization, dynamics, etc., etc. Okay? So we're getting close to the key question is, what are integration studies? So who's asking and why? So policymakers, they ask the question, how much will it cost? How much carbon reduction, etc. So the policymakers want to know the answers to all these questions. And because we don't have a system at the moment we have 1.3 gigawatts of wind, we plan to have 6 by 2020. And we plan to, we go from 1.3 to 6. We plan to supply 40% of our electrical energy from wind. We currently supply 13. So you're going into the complete unknown. System operators they want to know how to operate it, how to plan it, etc. So they have big questions to ask as well. And then there's market issues, which I think was covered yesterday with some people. I'm not going to talk too much about. There's all the issues about how you redesign markets, etc. The one key question about this, though, is that it's a sort of a chicken and egg situation. In order to answer these questions for the policymakers, I must take a view on how I do this. So this is really the research element, if you know what I mean. This is where people are wondering new operational paradigms, new ways to plan systems. And then you take that knowledge and you say, well, now I'll put those into models to answer the policymakers' questions. So in many ways, these questions rely on these things, and we don't even know what they are. So in many ways, it's a very inexact science. So the wind energy integration studies. This is a front cover of the Eastern Wind Integration Study in the US, which I think was published about 6 months ago. I was involved in this. This is the all-island grid study. I was involved in that one as well. So there's little operational experience with wind power, and looking for future scenarios and future. So what I mean by that is the policymakers want to know what happens if I put 40% or I get 40% of my energy from wind, and then we need to understand how we'd operate it. So it's sort of there's two levels to this. Okay. So integration, so EWITS is the Eastern Wind Integration and Transmission Study in the United States. AIGS is the all-island grid study. WWIS is the Western Wind Integration Study, which gets launched next week in Arizona. And EWIS is a European study, etc. So there's lots and lots of studies been done. So the studies require models and tools to quantify how we'll operate and plan systems. So that's what wind integration studies are. Any questions? Does that make sense?
When you say you get 40% of your energy, is that kilowatt hours or kilowatts?
Kilowatt hours. Yeah. So in kilowatts, it's actually higher than the amount of wind we'll have. It will be higher than our installed thermal capacity. Most statistics about penetration are generally on energy. They're not on capacity. Okay, so here you go. Remember I said before I showed you a graph that showed you. This was the 5th of April 2010, okay? This is system demand in Ireland. This is wind. This green line is instantaneous penetration level. So we were about to go to 50% penetration. So we're about to instantaneously be supplying over 50% of our energy from wind. And this was a preventative measure done by the system operator, because they're completely unsure of what would happen if we had a fault in the system. And some of the issues that Janos were talking about yesterday about synchronization, etc., are all very relevant to this. So this is the system operator taking the preventative action until such time as they know and understand what will happen. And that's a dynamics question. But you can see over this day, 33% of electricity came from wind, and it was going to go through 50%. So there are systems out there that do have very high wind penetration levels, and one of them is Ireland. And without going into details, we're connected to the UK by one HVDC connection. So essentially we're isolated. So these type of figures are probably the highest in the world for a synchronous power system.
I'm curious, I'm used to seeing the wind much more variable. Why is it so constant? In Ireland, it's usually beautiful burning motion.
Well, because it was blowing hard and all day. That's it. Sometimes more variable than that. But I mean, it was a very windy day. It was actually Easter Monday as well, and we have a holiday. If it wasn't a holiday, we would never have made this instantaneous penetration level. Now, the wind in Ireland is not that variable, actually. I don't think it's as variable as if you take Alberta wind, believe it or not, it's much more variable. And that's something to do with when it comes over the Rockies or something like that. Look, I'm not an expert in wind characteristics, I assure you. I wouldn't know whether it's more variable or less variable in Ireland than other places.
What was the installed capacity on this date?
1,300 megawatts.
Okay, so what's what's happening here is that the wind might be fluctuating between 12 and 25 meters
That's
a
right,
second,
yeah, but it's
which is a
maxed
huge
out.
fluctuation, but your power curve is perfectly horizontal.
Yeah.
You'll get exactly the same output from your turbines, whatever the wind speed between 12 and 25. So you might have very variable winds, but very constant power.
That's the characteristic he's talking about. So the wind may be varying back and forth here, but the power output is constant. That's probably what's happening in that instance. The problem is, of course, it's too windy, it all clocks out. So that's a big problem sometimes.
Although they can tape it
Yeah,
down to 35,
yeah.
can't they?
Yeah, no, they can. Any other question? Yeah?
Is this reduction in the generation of wind also related to what you said yesterday, that we may need more response in the future?
No,
in the
not
system?
not in this instance.
Okay.
But I'll talk about that later. This was the system operator has quite rightly doesn't know what will happen. So he's trying to. There's a study coming out in the next couple of months that will study all the issues around the dynamics at instantaneous penetration levels of 60, 70, 80%. What happens if we lose a large generator during one of these events? And until they understand that and have all the relevant precautions taken, they're being conservative, and they're right to be conservative. I mean, there's no other power system in the world has instantaneous penetration levels like this.
Western Denmark.
No, Western Denmark is part of the European grid.
Fair enough, yeah.
Well, it's not fair enough, that is the answer. No, but we're by ourselves. Western Denmark could lose every single piece of wind in one instant. It wouldn't make any difference to the European grid. 3 gigawatts, so what? It's irrelevant. We lose a 400 megawatt generator in here and we have no idea why. Yep.
So one of your questions must be about connecting Ireland to the UK.
Yeah, there's another interconnector been built right now. The second one, we have a 500 megawatt DC connector from Scotland to Ireland. We're building another one somewhere to Wales. And the next one I would suspect we might build to France. We of course are against nuclear as well, but as Jana said, you import it. I'm pro-nuclear actually, just to let everyone know. I'm pro everything that gives you energy. Any other questions? Okay, so some research questions, operation and scheduling. So here's a question. With large penetration of wind, should stochastic unit commitment replace deterministic unit commitment? So I'll explain a bit about unit commitment and things like that. I'll give some results and I'll give some questions and so it's sort of a mixed bag. So I'm not a mathematician, but so what I'm about to say I could be found out, so I've got no equations. Decided I'd leave all equations out. Don't go into mathematicians and use any equations, just leave them out completely. One of the ways we currently operate power systems is with a thing called, production cost modeling. One of the things that, when people say what happens if in 2020 you have lots of wind, one of the questions is how much does it cost to run the system, how much carbon. And there's a whole area called production cost modeling, which are these simulation tools that simulate how power systems operate in the future with different configurations. And out of them, after you do a year-long simulation, and you come out with a number that says this amount of fuel you use, this amount of carbon you produced. So production cost modeling is a well-known technique. But if you're going to do production cost modeling for 2020 on the basis of how we operate the system now, there's no way we're going to operate the system the same way we do now. If we have 6 gigawatts of wind installed in Ireland, we're not going to operate the system in the same way. We're going to have to operate it differently. The reason is that the wind forecast error over a period of 4 or 5 hours for 6 gigawatts of wind could easily be 3 gigawatts. At the moment, the forecast error could easily be 100 megawatts. So you're in a completely different paradigm that the forecast error is going to be huge. So the only real way of approaching it is to use some sort of stochastic optimization, or in this case, this is a scenario tree. And what you say is, I'm doing planning for the next day ahead, and I take the first few hours to be perfect. Then I take 3 different scenarios and I weight them with a different probability. And so some sort of scenario tree that tries to represent all the possible futures. And you plan the system to be least cost with respect to least expected cost with respect to all these possibilities. In other words, you come up with a robust plan that can deal with all eventualities, okay? Now, the unit commitment problem is an integer problem, which is which units do I turn on and off. It's obviously got a lot of, it's a stochastic problem because this is some sort of scenario. And it prepares units for a number of outcomes in a robust way. It's rolling as well. You're not going to just use one forecast and then leave it alone. You're going to use the most up-to-date information. So it's going to be stochastic unit commitment. It's going to be rolling every 3 hours. You're going to get a new forecast and you're going to update your plan. So it's going to be a much more dynamic, I mean that in a sort of activity way, much more dynamic situation than it is currently. Currently they do unit commitment day ahead, and they do revisit it during the day, but not as intensively as they will in the future. Okay? And the computational time of this definitely increases. But you have to feed this with something. These scenarios have to be generated in some way. And the way this tool that I'm talking about is from RISO in Denmark. It's called Wilmar. And these scenario trees are generated. They're generated with data, and the data comes from historical data about how wind behaved, how we forecasted, and what the errors were. And there's two different ways of generating these scenario trees: moment matching and scenario reduction. And I'll talk a bit about those later as well. So there's wind forecasting. We use forecasts. We do not do wind forecasting, so I'm no expert in wind forecasting at all. This shows you a forecast error. It shows you the measured, it shows you the predicted mean, and all of these show these sort of, so this is some sort of ensemble forecast. It says, this is what I think is going to happen, but there's a probability that these things will also happen. So it gives an ensemble. And using that ensemble, you should be able to produce a scenario tree. And using that scenario tree, you should be able to plan your system. That's the concept. And there's a project going on at the moment, an EU project called Animos. And what we're doing is we're taking these wind forecasts, which are ensembles, producing scenario trees out of them, running Wilmar on them, and scheduling the system. And the idea here is to try and see and test to see if in the future we could use, because at the moment we do not use stochastic unit commitment in power systems, we use deterministic unit commitment. But this is to try and see, if you're to try and implement this for real, what would happen.
So there's an assumption that there's no bottlenecks in the network here, and you can treat the total.
No, this I didn't show that, but you can include all the transmission network inside the unit commitment problem. I'm trying to keep this but no, the transmission system can be represented in this as well. So this is a very interesting area of research, because here it's forecasting. It's how you convert those forecasts into scenario trees that truly represent what's going to happen, how you do your stochastic optimization to act on that, how you calculate reserves. So there's a huge body of work inside this, okay? Inside this one diagram. There's an awful lot of, so it's forecasting, converting them into scenario trees, running stochastic optimization, calculating reserve targets, etc. So it's a very, very broad area, an awful lot of work going on inside that area in that one slide. Just to show you, these are, again, when you produce these scenarios, using ARMA and then scenario. So this is what the ARMA brings up, and then you use some sort of reduction technique, because you couldn't do a scenario tree with that number of scenarios. It would be crazy. But what you try and do is reduce it to a number of scenarios you can deal with. There's another way of doing it though, with moment matching. So at the moment we're looking at moment matching and scenario reduction and trying to compare and contrast them to try and find out which is the best one to use. Actually, it turns out, if you were to ask the question, which is the best one to use with regard to the forecast, you might come up with one answer. The real question is, which is the best one to use such that this outcome is best? We're interested in what's the best way of converting this information into scenarios so as this is best. We're not asking the question, what's the best way to produce a scenario so that best represents this? That's an interesting question, but it may not be the real question. The real question is, what's the best way to represent this so as the scheduling is the best? Yeah, Daniel?
Do you consider the reserve requirement as fixed?
No.
You're adjusting the reserve
Yes,
requirement?
it's dynamic. It moves. It moves on the basis because certain forecasts will be better than others, meaning that you're much more sure of what's going to happen, so you carry less reserves. So it's a dynamic moving reserve target at all times. Yep.
Why formulate it this way? Why not formulate it as a finite horizon optimal control problem? It would be, you get a feedback law the same way, and you'd have the same model reduction issues to deal with. That would be, then you'd be in a context where there's a lot of results in approximate dynamic programming.
Sorry?
Yeah, approximate dynamic programming, there's a huge literature. So if you model this as a finite horizon optimal control problem, you have a lot more tools.
Well, I mean that's why I'm here. I mean there are other ways of doing this, for sure. I mean, but at the moment, the Wilmar tool was developed in an EU project. It has been used on 2 or 3. It's currently been used on the Eastern Wind Integration Study in the US. It's used in several integration studies. It was purpose built. It's a very good tool. I'm sure better tools can be developed. At the moment, I mean, we're not. This was developed by a bunch of operations research applied mathematicians individuals. It's good. It's robust. It works very well. If people want to develop a better one, then they should try and do it. I like this tool though because it was purpose built for wind. It was from ground up, it was written, it was coded from the start with the wind in mind. So this whole idea of rolling was very important. The whole idea of the scenarios was very important. And in fact, it's all the time been improved at all times. But there's a very, very fruitful area of work all in there, in all aspects of it.
It generates trees directly rather than just scenarios from the root and then leaving it to you to see how you can branching tree like this.
Well, what we're actually looking at is the different techniques at the moment of how to produce them.
But does Wilmar just produce individual scenarios from an initial condition?
No,
Does it produce
at the moment, Wilmar is run as a planning tool, which is what happens in the future. What we're trying to look at here is how you'd use it in an operational sense, which is, in this comes, you don't have an awful lot of time. You're not going to be saying, give me 4 days to work out what the scenarios look like. The forecast comes in, and within minutes, you're going to have to get the scenarios out the other side. So how do you produce the scenarios quickly? These scenarios have to represent this as best as possible. So as this result is as reliable and as economic as is possible. There was a question at the back there. Blue.
Yeah.
It's a very useful tool. No, man in blue.
I was noticing your time scale at the bottom. Is this done on a 12-hour, 6-hour?
It's done on a 36-hour basis, and it's rolled. Well, at the moment it says rolling period 3 hours. We can roll it. Actually, I'll tell you something. We can roll it now every 15 minutes if we want, but we haven't got that here. So but 15 minutes I think is a bit excessive, and we do it for 36 hours ahead.
Right. So that was going to be my follow-up. So what's needed to cope with the uncertainty? 15 minutes enough?
I think 15 minutes is excessive, but we decided to go down that far because that's one of the questions. Is 3 hours? I'll show you results later on where the model error, because we're only doing 3 hours, has a perverse result that people look at the result and say it's wrong. It's actually an artifact of the modeling which has to do with the 3 hours. So when I come to that, remind me of that.
Mark, the forecast, about 7 hours, the forecast error seems to be huge, while for 15 hours it's much smaller. So I would expect the error would be larger.
I got this off what's his name, Hans Giel. It's just a slide. I mean, I'm not saying it's real data. It's just a nice, pretty picture.
Could also be the same.
Huh?
Did National Grid see similar effects where there are some types of weather where the forecast is just naturally more accurate?
Yeah, look, I mean, I'm not here to talk about forecasting because that's not, I know as much as the next man standing in the bar about forecasting. Any other questions? Yep.
So how would in practice the people that submit their bits, they submit a day ahead bit and then they submit their curves saying this is my minimal uptime, or
yeah,
they submit a bit every 3 hours and update it?
So you're talking about the market aspects
yes.
of this. We don't generally deal with them well. I mean, they're very important, but we generally tend not to concentrate on those. But I do know that some people have tried to use this. Think about this. Could you use the same model to run a market on? Now, Yanis is shaking his head because the problem with this is day ahead at this point here, there's 9 different prices depending on what happens. But there are people who are looking at it and wondering about it at the moment. I'd have to agree with Yanis, you couldn't use it. So you may use it in an operational sense, but you may not use it in a market sense.
You might maybe have, but this is just speculating. You might have bits of saying this is my curve, this is my requirements. I mean, for this much uptime, I give this price and so on. So.
Yeah, that's true. You could have that. Wow, I'm only halfway through the slides. Man at the back there.
How many scenarios are you evaluated? So tens, hundreds?
9.
9.
Well, sorry. I mean, okay, how many are we? I mean, you can ask these, you can ask the wind forecasting community to produce an ensemble, which is just a range, and they can produce as many as you want. The simple fact, from a pragmatic point of view, you can't deal with, in the scenario tree, you can't deal with hundreds. So in this particular case, we reduced it to 9. But again, it's a question, how many do you need? I would suspect 9 is fine. Again, I mean, I think at the end of the day, this idea of getting this to represent this perfectly is not the question. It's getting this to represent this in an adequate manner so as this is good. That's a much more sort of, you know, practical question, which is, I don't care if someone says to me, oh, listen, the moment's at 3 hours out of a small error or whatever. It's the question is, does that really make any difference to the operation of the system? Because you've got to remember, this drives the operation of the system, and some of the characteristics in this are actually irrelevant. Some of them are relevant, and we don't really understand which ones are more relevant than others. One more question before I go on. Was one.
In order to use this method to prevent the need for explicit reserve criteria, then you need to have a pretty low percentile worst case scenario with a pretty low probability attached to it. I'd like to ask how you generate that worst case scenario.
I mean, the question, I'll rephrase the question. One of the things about this is that you could just use this technique and carry no reserve, have no reserve target, because the system would say, if I've got to meet all these possibilities, inherently it carries reserve, because if it says I have to deal with this wide range of possibilities, it makes sure the plan is robust with regard to all of them, ergo it carries reserve.
But have you captured enough cases to cater for the one in 6 months worst case wind drop, for example? That's the worry, with only 9 scenarios.
Yeah, but I mean, sometimes you're going to get caught out. I mean, do you want us to operate the power system so we're never caught out? Do you want to see your electricity bill, do you? At the end of the day, the odd time we turn off people, it's you know, that is good. You know, if we never
quantify that?
Huh?
How do
If
you
we
quantify
never turn off people, it's very bad. It means we've overbuilt the
Yeah,
system.
but how do you quantify that? How many people are you willing? That's what he's asking. How do you model that question?
What's the percentile of your worst case scenario?
I would say, being practical about this, that power systems currently are operated in custom and practice mode. Despite all the statistics they use, they basically say, hey guys, last year it worked. So let's continue to do it. Sorry, I think that's the way they do it. They do lots of analysis, but at the end of the day, it comes down to people saying, last year we didn't get in trouble with the government or the regulator, it works. All this analysis that people, you know, do is just reassuring. That's all it is. It doesn't actually translate. I mean, the reality is the chief executive will decide. So I know what your question is, but the answer is some human being will make a business decision. And if someone comes in to say, hey, listen, we can make it more reliable and here's the cost, and you'll take a good instinct decision and say no. I don't think you can quantify those things.
I'm surprised you don't solve the opposition problem with a, say, 1 gigawatt constraint of reserve. I mean, why not? Just based on some prior knowledge.
This, the way we solve it is we have 400 megawatts of reserve carried always across all these scenarios.
Okay, yeah.
Oh yeah, no, we do have a reserve constraint for the instantaneous loss of the largest unit, embedded within it. But then the thing about it is how it deals with the scenarios is it tends to overcommit units, which effectively is carrying more reserve. I'll continue because otherwise I'm only halfway through the slides. Let me just give two results. If you look at the performance of these schedules and forget about perfect. Perfect doesn't exist. There's no such thing as perfect. Okay. So if you look at the two, stochastic and deterministic, what you find if you run the system stochastic, this is demand not met. This is your value of lost load essentially, or whatever. This is reserve not met. This doesn't mean you're in trouble. It means if something happened during those hours, you'd be in trouble. And this is replacement reserve not met. Fundamentally, the deterministic runs are less reliable. In other words, the stochastic approach makes the system more reliable, which is what you'd expect. And in addition, the stochastic runs, this is again, it's the same color code as before. These are costs. Forget about the perfect, it's not relevant. But the stochastic is cheaper, so it's more reliable and it's cheaper. Okay. Now back to this artifact. The reason why the stochastic cost starts becoming close to the deterministic cost is because at this point we're rolling it every 6 hours. Okay? As we roll it more often, let's say 4 hours, we're using more up-to-date information, which means we're getting a better answer, which means the costs reduce. Okay? And then you see it go up like that. And when I saw this, I told the PhD student he was wrong. But he wasn't. He was right. Because what's happening here is that because the way the scenario tree tool works is it's assuming the first 3 hours are perfect, okay? And in reality, they're not. And so what's happening here, this is an artifact of the modeling. It's not actually real. So you want to be very careful about what you report, okay? So as you roll it more often, you get more up-to-date information. But then as you roll it more often again and again and again, what you're doing actually is, in comparison with these hours, you're capturing more of the uncertainty. So in fact, at 6 hours, you're assuming the next 6 hours is perfect. At 3 hours, you're assuming the next 3 hours is perfect. At 1 hour, you're assuming the next 1 hour is perfect. As you come back this way, you're actually modeling more of the uncertainty. Uncertainty costs money, and that's what you're seeing here. So in fact, that's an artifact of the modeling. Does that answer your question to some extent? Yes?
If you were modeling this with a deterministic unit program, where we had a high reserve for, say, 4 hours ahead, to model the uncertainty,
yeah,
and you rolled you kept repeating the deterministic unit problem every few hours,
yeah,
up-to-date forecast.
Yeah.
How good or bad would the comparison be?
That's it there. That's what we did with that. That's deterministic unit commitment rolled using just simple, well, straightforward reserve targets. It's not scenario based. So that is what it looks like. And the reason we use these as well is we made sure that, you know, they are effectively the portfolios are identical in terms of reliability. So we're comparing like with like. So but I mean, I think everyone will accept that if you use stochastic optimization, you will get a better answer because you're using more information than you are if you're using deterministic. But we are rolling it here. Okay. How long do I have, Chris?
Nominally 25 minutes, but if people are having fun, I don't see any reason why we should not run over.
What about me?
Oh, you're
oh. I've just been elevated to a person. It's great. Okay, so just conclusions, because I want to get, there's other issues I want to cover as well, and I'm glad to discuss these with people afterwards. So the conclusions are, stochastic optimization I think is probably definitely a good thing for wind. It's an open area, a lot of interesting work to be done there. The wind has to be modeled, it has to be forecasted. I didn't say too much about that, but there's obviously a whole area of forecasting. And then in my particular instance, I'm saying we need to produce scenarios out of those, etc. And operationally in the future and for production, so there's two reasons. We have to actually develop the actual tools and techniques we're going to use to operate the system. And we need to have some idea of what they are now so as we can answer the policymakers' questions. So it's sort of like I need to develop tools and techniques that I think are going to be used in the future so as I can answer some of the questions of the policymakers, but I also need to refine those tools and techniques for reality when it happens. And they're two subtly different things, but they are related. So that's the conclusions for the operations. What about planning transmission? So with large penetration of the wind, should transmission planning practices change? So this is just a simple map of Ireland showing the transmission system. Most of our wind is on the west coast, and the transmission system, if you look at it, 400 kV is the high voltage system, 220. Most of the transmission, good transmission tends to be around Dublin, not around here. So if we want to build lots of wind, we have to build lots of transmission. Okay. But the question is, do you build it as you traditionally built it? In other words, do you build it as if, like, you know, a 1 gigawatt nuclear plant? Do you build it so as you're always able to take the nuclear output 24/7? The answer is probably no. This is a very simple illustration. It was actually done by a company called Electricity, and they use it in a submission to regulator to show this is wind output, this is load, and these A, B, and C are the three traditional planning points that the system operators used to use. Winter peak, summer minimum, and summer night valley. And they traditionally would use 3 points in the year and say, I'll plan the system around this. But if you can see, you know, this is the I mean, how often do these hours actually occur? Very rarely. So it's trying to make the point that deterministic, sort of just picking 3 points and planning the system may not be a good idea, okay? And that's part of the discussion that people are having at the moment. The other thing, just to remind you, that if you take the capacity credit, it's seasonal and it's diurnal variation. It's not like a nuclear power station that is essentially 24/7 flat line at, you know, and full output, okay? It's a different beast entirely. So from reliability point of view and from a capacity factor point of view, it's different. Should you plan the system differently? The answer is probably yes. Some other things about it though, just this whole issue of farm A, farm B, they're obviously related because they're geographically close together. So strong dependence in general, but slight phase differences. If you put them in another way, here, this shows farm E and H. Where's E and H? There's H and there's E. And again, this shows the correlation between it, but it also shows that sometimes, you know, down here, there's quite a few points where farm E is pumping out max and farm H is pumping out zero. So it's not a, you know, there are cases where they are not correlated, essentially. And what this means in terms of planning this system, traditionally what they would do is they'd do some dispatches on the system and say, this unit's doing this is doing that, and be based on some sort of unit commitment. But with wind, then what are you going to do? How are you going to represent a few cases that you decide to plan the system on? It becomes much, much more difficult. In the traditional way, the worst time was probably winter peak. You would know at winter peak, every single unit in the system would probably be full on. You'd know roughly what you were getting. With wind, you're not too sure what you're going to get. So, here's a question. Merging operational and planning timeframes. You know, how important is it in planning application to model operational timeframes? So in other words, instead of just picking 3 points, should I actually try plan the system at every hour of the year? 8,600 whatever hours? That's a question you should ask. Yeah? And it's a question that we've actually asked, and it's a question that we've done some work on. And the question is what happens is if you try and do that, you end up with a very, 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 very large optimization problem, which you guys know about. And this is just a very simple illustration of it. Can you decompose it? So here's the investment problem and here's the individual problem. So can you decompose it? And the answer is if you make certain assumptions, you can. But are those assumptions too, you know, are you making assumptions that are not really valid? That's a whole open question, is how would you plan transmission systems taking into account every hour rather than just 3 hours of the year? And with wind, you may have to do that. I'm not saying you have to do it. So there's a very interesting area, very large. Like these are problems which, you know, I know hundreds of thousands tens of millions of constraints, and you know hundreds of thousands of variables, etc. And here's another thing, uncertainty. I mean, some people, if you just take, say, people plan systems, if you just take this simple case here, it says, if you take different values of, if you take different costs or prices for fossil fuels, you get different dispatches on the system. If you get different dispatches on the system, you'll get different patterns on the transmission system. So how do you plan under uncertainty? I mean, the future is very uncertain. So there's this is trying to illustrate that if you take different values for gas, you'll get entirely different answers for the prices. So which version of the future is most likely? But how that impacts on the transmission system is shown here. This is a transmission line. It's showing how it's loaded over a year. And it's showing you that there's different, if you use different forms of unit commitment and different variations. This is a very simple representation of unit commitment. This is a very complicated, or let's say close to operational. This shows you the difference that fuel prices make. So is it better to take into account the uncertainty or the details of the operations of the system? Because if you look at it, the price uncertainty of the fuels will have a bigger effect. So some people go in and say, oh, operationally I'll have to represent exactly how the system is operating in a unit commitment sense. I'll have to take into account all my stochastic optimization, all these constraints. And you go to a lot of bother and get this answer. And someone tells you, well, the price of gas has just increased by 20%. It has this effect on it. And you can see that the effect here is much greater than here. In other words, you can sometimes do too much detail and something else comes along and is so uncertain that it makes no difference. And I think that's a very, very, very important point. I think that some people get really stuck into detail and they do lovely work and you suddenly say, well, what happens if the gas price changed by 20%? The answer is all your results are wrong. So maybe you shouldn't take into account all the operational issues because the uncertainty around fuel prices is so much that it doesn't make any difference. So I'm just throwing out sort of interesting things that may stimulate some thought. This is a test, just to do some work that we've actually done on this. This is a test network And what we did is we asked the following question. We said, on this network here, I want to install wind. The people are saying pylons out, I can't build any more transmission. And the question is how would you install the wind so as to get the optimal amount of wind onto the system? And what that means is that if you put wind in certain locations, you can congest the transmission system. Some wind is better than others, so it's a trade-off between the location of the wind and the quality of the wind, okay? Now, results, and if you, I think it has, I don't know, it's got 450 million constraints or something like that, the optimization problem. But if you then do this and solve it at each of these points, if you say I want 5% energy from wind, 6, 7, 8, 9, up to 10% energy, at 10% it becomes infeasible. You can't actually get 10% out of this unless you curtail the wind. And one of the assumptions we said is you weren't allowed to curtail the wind, which is, that's actually a completely academic assumption. We will be curtailing wind, let me assure you. And we'll be curtailing lots of it. But it's interesting to see that if you only wanted 5% energy, you'd put 93 megawatts there and 81 there. But if you wanted 8%, you wouldn't put as much there, you put less there, and you put more there. The basic point is that as your targets for wind energy increase or change, the pattern that's optimal to locate them on the system is different, which says that if you can't build too much more transmission, you should pick a target in the future and stick with it. Because if you don't, in other words, the pathway, if you were to do this, yeah, at the first instance, that is not optimal in this case here. So that's a policy decision. If a policymaker say, what's the best way of using the transmission system? The question is, how much do you want? And if he says, well, I want 5 and I want it to be optimal, and then I want 10 to be optimal later on, you can tell him you can't have that.
There's any way of seeing intuitively why this happens?
Yeah, I mean, what happens is that this wind farm here is the best from a capacity factor point of view. It's the cheapest wind. But the problem is, as you try and get more and more wind energy onto the system, this one here is in a location that causes transmission congestion for the other wind farms. So it's an interaction between them.
Just briefly, can we take only short clarification questions during the talk? It would be very good if we can at least finish Mark's actual talk by the scheduled time of 5:15, even if we can't get all of even if the discussion afterwards rolls on.
Is there a clarification question at the back?
Essentially, it's a very brief question, which is a clarification. Presumably that's actually rather similar to the previous slide, in that instead of the price of gas changing, if the politicians decide you're going to put in an extra power line, then all that changes.
Yes. Oh yeah, absolutely. Yeah. And sorry, this is a very academic study because we didn't allow any curtailment. We've redone it. This is published. We're actually about to submit a paper that allows curtailment on the same basic idea. So we didn't allow any curtailment. We didn't allow anything to build anything. But it proves the point you can locate the wind in an optimal manner. But someone better tell you how much wind you want. Okay? I think it's a very important. I mean, one of the things in an awful lot of these grid integration studies is the target. You know, if you take a 10%, 20%, 30% target, the transmission system that you need for each one is somewhat different. And building for 10% is probably a waste of money if you're eventually going to go to 20%. You'd build a different type of transmission system. So it's up to politicians to make decisions. And like someone said yesterday, if you're going to try and model them, good luck to you. Back to the social scientists. So conclusions of planning and transmission, wind characteristics indicate no need for firm access. Sorry, I didn't really, that was, there's some hidden slides in there. I had 70 slides this morning. I hid some slides that point has to do with that. Optimization of planning is possible to get the best use of the network. Merging operational planning is feasible, but may not be necessary. Not too sure. And planning under uncertainty, a very important issue. So I'm raising just questions here. Generation flexibility, planning. I just want to raise this very quickly. I've used this slide for 5 or 6 years and it's pretty ageless. Mind you, this is the financial consultant, all the eggs in one basket. Recently that has not been that has not worked. But the best analogy is, you know, if you wanted to go to the store for a bottle of milk, you can drive your Ford Focus. You can drive your Lamborghini as well, but the Ford Focus would do just as well. The point is that in a power system, you need a portfolio of generators. Some need to be the Ford Focuses and some need to be the Lamborghinis. But what's the balance that you need between them? And the whole issue of flexibility is key. I think it was mentioned yesterday. if you take Ireland today, this is 15-minute deltas, 15-minute changes in net load. This is wind and load together, because wind, you can take it effectively as negative load if you want, okay? And you can see that with load and net load, there's not much difference. In other words, the brown is with wind and load, the blue is with load alone. There's not much difference in that distribution, is there, at the moment? This is 2009 data, okay? But if you go to 2020, you can see a dramatic difference between load and net load. Basically what it's telling you is you're going to have far more very, very large changes happening over very short periods of time. And this matter was mentioned yesterday about BPA and things like that. So for example, if you, this is for Ireland, so you're going to have more changes. So the whole issue is about this. And I'll just use this one slide, the flexibility paradigm. So you have sources. These are sinks for flexibility, load, solar, wind. They'll cause the need for it. The sources for flexibility, demand side management, storage, interconnection, conventional generation, and what we call matchmakers. I mean, transmission networks are not sources of flexibility, but they allow you access sources of flexibility. Fuel storage, this was mentioned yesterday as well, fuel storage. And there's a whole institutional issues about forecasting, gate closure, grid codes, unit commitment, and ancillary services. If you take this whole thing together and say, can I have a metric for flexibility? Nobody knows how to do it, because it's very, very difficult to try and say, do I have, in other words, if I gave you an electricity system and said, I'm going to have 8 gigawatts of wind in this system in 20 years' time, do you have enough flexibility? I'm not talking about do you have enough capacity, I'm talking about are the units you have flexible enough? And the answer to that question is very, very difficult. In fact, I don't know anyone who's actually solved it. We've tried, and we've come up with some solutions to it. And if you take the capacity credit, this is essentially how much adequacy does wind bring to the system in terms of serving load. There's another question. Do you have enough flexibility in the system? This is a question that says, do I have enough capacity? I could give you a power system that has nuclear power and wind together and hand it to you, and you do a capacity calculation with regard to adequacy, and the system is perfect. It's fine. But you ask the system operator, could he operate it? And you say, no, can't operate it. And there's no reliability statistics for that. There's reliability statistics that say I have enough generation. There's no statistics that say, is what I've given you operable? Can I operate it? And there's no such statistics. Now to calculate those numbers, I'll just give you a little illustration. We're doing a technique that's effectively the same as capacity credit, but it's based on flexibility. And we're coming up with, this is a tease the mathematicians. It turns out it looks like to calculate flexibility for power systems, you definitely need to model the operational issues. You can't get away with it. So in the planning there for transmission, I sort of said, I don't think you need to be too bothered about the details of operations. It turns out in flexibility, I think additional unit states are required. I think it looks like you have to model the operational issues. Once you have to model them, you get numbers like this in terms of the data and the analysis that you need to do. And you're getting run times for these things of 17 hours and things like that. So there's another, flexibility in power systems, very important area. Everyone's talking about it. It looks like computationally it's very intensive. So merging operational planning may be necessary, large dimensional problem planning with certainty. So I've got 10 minutes left. Sorry, is there any questions on that? I went through that very quickly. Flexibility is probably the single biggest issue in power systems at the moment with regard to integrating renewables. But no one has a number for it, a metric. No one can tell you this system is flexible enough. You can't give someone I can give someone a power, if I give power system over to Chris here and say, is it adequate? He'll do a calculation and say yes or no. If I give it to him and say, is there enough flexibility in it so that it can be operated? He'll look at it and say, I think so. But he won't be able to put a number on it. And so trying to put a number on this is very important.
Well, I'd bring up an engineer, because at the moment this judgment is something that an experienced power systems engineer can make good judgments on. But
we're not replaceable.
we don't yet have the mathematical methods to do
and
that.
To be honest with you, I don't think he ever will, because I think that this problem is so multifaceted that it's just far too difficult to model. What do you mean by flexibility? Quantify it. It's very difficult. But we're attempting it. Okay, now the last thing I'll do is dynamics, frequency control. This was spoken about yesterday, so I put these slides in. This is another analogy I have. So you can think of a power system as well like this, that they all collectively drive one shaft, and that collectively drives some sort of common load. That's a way of thinking about it. These blue things are synchronous generators, and you can think about them as being connected. Oops. You can think about them being connected to system by chains, so they're a very tightly connected system. You introduce these things called wind turbines. They're green, of course, naturally. And you can think about them being connected to the system by an elastic band. It's only an analogy now, don't shoot me here. So this is a way of thinking about it. If you introduce these devices, which are doubly fed induction generators, which are the more modern wind turbines, they are also connected by essentially an elastic band. But also, if you notice, they don't add to the length of the shaft, so they don't add to the weight of it. So as you add more and more of these, this shaft becomes smaller and lighter. As it becomes smaller and lighter in terms of controlling it, the frequency deviations become larger. And this is something that was mentioned yesterday, so I decided to put it in. And if you look, I'll skip over that for time reasons. If you look at how the system responds then, if you put lots of wind in the system, the frequency response to the system is such that with lots of wind, the frequency falls further and faster. So this green one here has lots of wind, and it falls further and it falls faster. And this is the whole issue of inertia on power systems. And the Irish power system, being an isolated power system, is the system in the world that has this problem. It will have this problem much more severe than anyone else in the world. And
so that's frequency response to what sort of event?
That's a 400 megawatt CCGT tripping out in the system. Okay, and just to show you, I'm not going to go into huge detail. This is historical data of real events that have happened, and without going into it line by line, we have experimental evidence that this is now happening. We have found that if there's more wind in the system, and if we do have an event, on average, the frequency is falling further and faster. So we're already, these are simulations. This is real data. This real data is starting to tell us that we are actually starting to see this happen. Okay, so it is actually happening. And actually, just to point out, the FERC in the US are doing a study on this for the United States at the moment. And I was involved in that, and the report is not out yet, so I can't tell you anything. Mind you, if you ever have to go to the FERC in the United States, it's more difficult to get into the FERC than it is into the White House. Having been in the White House and the FERC on 2 different days, it was easier to get into the White House than it was to FERC. But anyway, that study is coming out shortly. So even though the United States is a huge system, they've looked at this issue on the United States system. So we're starting to see it already. And that's more experimental data. I won't go through those. And this is something else I promised yesterday. This is something I can't tell you the full details of this because the report's not out. But remember I was telling you yesterday about the largest event? It turns out that fault ride-through, if you have enough wind farms in one location or geographically and you get a short circuit, and if they all obey the fault ride-through requirements, they do exactly as they were told, it turns out that could become the largest single event from a megawatt point of view. This is essentially that's your fault ride-through happening there. And the amount of energy that's lost during this period of time is so large that it makes the frequency drop to 48.5. In other words, it's actually from a point of view of losing a generator, it's a worse event than losing the generator itself. So what happens is a short circuit, all the wind turbines do their fault ride-through, which is what they're supposed to do. And during that, they can't get any megawatts onto the system because their voltage is dropped. And the amount of energy we lose during that period of time is so substantial, it could actually be the largest single event in the system. But big question mark, not sure about this, more study to be done, etc. So
what's the difference with respect to synchronous generators?
Sorry?
What's the difference with respect to synchronous generators?
Because the synchronous generators tend to be closer to the load, so the load will also drop as well. These are off on the west coast, and there's no load. So we're not getting the load benefit. That seems to be what's going on. But it's open to, that's typically what happens, Janice. You get a short circuit, you have load and generation both drop, so the load consumes less, the generator produces less. This is a case where the wind is by itself with very little load, which is what will happen. Scotland will have lots of wind but no load. The middle of the United States will have lots of wind and no load. So these short circuit events could actually become megawatt events. Now it's a big question mark. I'm just putting that up because I said I would.
So it's not the question of technical characteristics of wind, it's the question of the distance from the load.
Yes. And it's a question that maybe the grid codes should be even tighter or different. We don't know. But that'll come out soon as well. So, yeah, not clear what the mathematical challenges are. I just thought, I mean, I think this is an area that some people talk about, you know, these are engineering issues. I think we know how to solve them. There's other dynamical issues that, you know, that Yanis was speaking about that are relevant, but I think this one is probably something that, it's but down to solve the relevant problem, guys, okay? Maybe there are some problems there that are interesting, but do not need any additional mathematics to solve them. So, last thing, human behavior, the sociologist, yeah? This is the 14th of March 2009 versus Saturday the 21st of March. It's a rugby match, yeah? It's when Ireland won the Grand Slam. Not this year, unfortunately. But you can see what happens. I mean, obviously, you know, this is the Irish load, so, you know, people are watching the telly and all the rest of it, and at halftime they boil the kettle. You've all seen this before, so it's human behavior. But that human behavior is very predictable, isn't it? You know, Ireland are playing the Grand Slam tomorrow. The TSO knows it. They'll plan accordingly. But there's one group of people in the world that no one knows what they'll do.
It's your daughter.
That's my daughter. That's the reason I can use this picture, because she's my daughter. Yanis knows she's my daughter because he's met her. Teenage girls change the world. No one knew 20 years ago that there would be a thing called mobile phones and an application called text messaging that teenage girls would drive the entire telecommunications industry. No one knew it. And in fact, text messaging was not an application that someone dreamed up and said, here's an application that I can sell. It was an application dreamed up by Ericsson's engineers who were deploying the GSM switches and decided to build this application as a little facility for themselves. That's why it was developed. It was developed as an internal application for the engineers who were installing these GSM switches across the world. And all of a sudden someone says, I wonder would the customer like that? And now, I don't know, how many text messages are sent around the world every day? Are you sending one now, are you? And the largest single senders of text messages are teenage girls. So, the point I'm trying to make here is that in energy systems in general, right, one of the single biggest things will be how people will use energy in the future. Will they be responsive to load? And it has nothing got to do with old farts like Janis Bialik or me. It's got to do with teenage girls, because they are the future. And you know, old fuddy-duddy mathematicians in Cambridge or engineers in Cambridge are not going to be able to tell you what these people are going to do. So there's a big uncertainty out there, and maybe the social scientists might be able to tell us something about it. So conclusions, wind penetration levels are increasing dramatically. Operational planning paradigms will change. Opportunity for certainly large dimensional problems, optimization under uncertainty. They would be the sort of key areas that I would see as being for the opportunities for sure. And questions. John, look at that. Go West.
Good stuff. Thank you very much, Mark.
So, any further questions? I think we can run over a bit with there aren't any more scheduled until the afternoon, and lunch is until 1, so I think we can run over with questions, but if anyone needs to go to another appointment, then please feel free to do so. So, questions? David.
Mark.
I was wondering when you were going to ask me a question, David.
Well, here it is. In your planning, you showed that where you put the wind farms would depend on where you eventually wanted to finish up.
Yes.
And my question is, how much guidance do you get from nodal pricing? Or do you not get much and you have to step back and do the whole system optimization? How can you decentralize this problem, is another way of putting it.
Yeah. Well, first of all, that analysis was done with no curtailment, i.e. no congestion. So that's a very abstract problem we did, okay? So that's the first answer. In other words, I'm not saying that this is true in general, I'm saying it's true for that particular case. So I'm not judging the question. I don't know the exact answer to your question. But how can you decentralize it? That's a better question. I was in the IEA last Friday at a meeting where some very senior people in the industry came to the following conclusion. They said, well, look, with all this renewables coming on the system, you know, we're talking about desert tech and offshore grids and all the rest of it, maybe, just maybe, the centralized approach is appropriate. And I think that's the answer. I think if society wants to build this amount of renewables, transcontinental transmission and centralized planning is the only way to go.
Well, I'm sympathetic to that hypothesis, but if you're going to make a policy decision which may cost in this country £1 billion or so, it would be really nice to do some simulations to say what would happen if you chose the decentralized market-guided approach, or the connect and manage approach, or whatever, or let's go for the single buyer model. Because these are dramatically different models, and the cost of compensating the
But
people
billions is only, I mean, SSE have decided to spend 15 billion themselves on offshore wind, haven't they? So it's not billions we're talking about tens of billions here, aren't we?
Well, every billion helps.
Yeah. Well, the answer to, I think in these issues, these are such grand challenges, I think. Listen, the US put a man on the moon. General Electric didn't put a man on the moon. Yeah? And nor did Boeing. The US put a man on the moon. What they did is they got all these people centrally and said, let's put a man on the moon. Yeah?
Well, and the CEGB gave us 3 different incompatible nuclear power station designs for AGRs.
That's the CEGB for you.
Central planning.
Yeah, oh yeah, I mean, I'm not... Central planning without governments is a good idea. How about that?
I think they did that all by themselves.
First of all, if you did your simulation, if I did my simulation, we'd have totally different answers, because in my competitive equilibrium, I'd have prices going to $200,000, and in another person's simulation, price would be marginal cost, and you can get completely different answers. And then there's the reality that the possible, it's best back to the social sciences comment, that the range of behaviors of the thousands of market agents is so large, and the sort of manipulations that we could never foresee. I mean, we designed the California market, and you can say, oh, it's just the problem with the grid. But no, we didn't forecast that Enron would decide to do the repairs in the generator in the middle of the day. Without a lot of constraints on the agents and the system, the range of possible behaviors is so big, we couldn't ever simulate it to really be sure that we have a reliable system. That's my feeling.
So you're a pessimist.
But I just think the complexity is so great, and the reliability is so important, that I don't know how we could do a simulation study that would have the confidence margin we need.
So what do we do?
So that's why I think we need to put constraints on behavior, and then it becomes a more predictable system.
No, but I mean, given that you have to make a decision now, the government in the next probably 12 months will decide, do we go to the single buyer model of central planning of everything, or do we try and fix the market that we have?
I think you
now,
can have
these are radically different alternatives.
It's not one or the other. You could have a market that's much more constrained. Where, for example, a generator is not allowed to commit and then change their mind and sell to Norway. If you put a lot more constraints in behavior, it would be a more predictable system, and then I'd have more faith in a market, less centralized.
Has the UK market failed, has it?
Yes.
It has, hasn't it?
I think Ofgem admit this now, don't they?
My God.
Now saying it needs more central planning.
Is everything perfect here? Well, we only failed.
20 years of waste, isn't it?
I'm not going to get into market discussions. It's not my expertise.
Yeah, this could be a good one for the panel session later. We'll have both.
Sorry,
we'll have both National Grid and the regulator.
The reason I brought up this, in the US, a big debate. All the wind is here, right? All the load is here, okay? And if they want to go to 20% in the United States, they're going to have to build transcontinental transmission. And they're not going to have to, I mean, if they build 345, it's useless. If you build 800 kV HVDC network overlay of the whole thing, the price of it per unit of electricity is incredibly cheap. But if you build it piecemeal across states, or allow each state to build their own bit and pieces, you end up with a 345 spaghetti junction thing, very expensive, very unreliable. If the US wants to do this, Mr. Obama is going to have to make a federal decision, and he's going to have to overrule the states. And that's it. Because wind here to get to California has to go through Utah. Utah gets no benefit out of it, therefore they will not allow any to build transmission through them. If the United States wants energy security and green energy, it's, sorry, Mr. Utah, we're building it across your land. So, to do these, and you've seen Desert Tech, you've seen all these big plans for offshore grids, whatever. It's not going to happen piecemeal. It can't. It's inefficient and it will not work. So I think we should have a dictator for a few years. So David, David can become the dictator in the UK.
Well, I'm happy with the idea that the transmission grid, which in this country is integrated and can do central planning, providing you are allowed to build anything anywhere, and does have the ability through its connection charges to indicate where it wants generation to connect. But then the politicians come along and say wind should get the same price anywhere. And they're allowed to connect. And it's that combination of politics which is completely at variance with the market that creates huge problems.
When I'm saying centralised planning, I'm saying centralised planning with some good economics.
How do you get that with politicians?
You get rid of them. No, I think we should make David the Prime Minister for how long? 3 years?
Mark, the question of the frequency response, the system gets lighter and the frequency response gets cheaper, gets steeper, gets worse. But with the DFIG double-fed induction generators, you can actually do controls in such a way that they pretend to be synchronous generators. So there are technical fixes to some of the problems we've been talking about.
Yeah, and I skipped over that because I didn't have much time, but I have the slides here. So let me show that. Yeah. There it is there. I mean, it's only showing the response. There's the synchronous generator. There's the fixed speed generator. It does a sluggish response. There's a DFIG, do nothing. The blue one is a DFIG with supplementary control loop. So you can actually solve the problem by making the DFIGs respond. However, GE have claimed they have a product called wind inertia, and yet when you get them on the telephone and ask them certain questions about it, they're a bit evasive about some of the answers. So I've yet to see it, until such time as you see it work in the field, such time as the TSO gets comfortable that they will actually respond as they say, it is not it is potentially a solution. There's lots, sorry, that's what I said about this. This is not a mathematical question, this is an engineering question. There are solutions. Supplementary control loops. We have problems with our rock-off relays. We'll end up with a cascade effect because of rock-off, so we have to be careful about that. So there are solutions for sure.
Gotcha.
Oh no, you.
No, please.
No, just a quick question. It seems obvious that you would have adjustable flywheels on windmills. There's some, very.
Do you want to pay for them?
They're very expensive.
Yeah. Flywheels, as an engineer, Beacon Power has a beautiful flywheel. It's an incredible device. As an engineering project, it is. It's got material science in it. It's got power electronics in it. It is a wonderful device. But so is that Lamborghini.
Yeah,
but I can go to the store and get a bottle of milk with the Ford Focus. So I don't think flywheels are, in certain applications they may well be an answer, but I don't see them in mainstream. Very, very expensive.
Just thinking about the slide you had of the different model runs with different wind penetration, no curtailment, and showing that if you optimize for 5%, that's actually something of a dead end for 9%, instead of sub-optimal.
Yeah.
In the runs with curtailment, do you still see that dead end effect?
Yes. Yeah.
Right. So
it's not as dramatic because we can curtail, and there's also issues around that, but it is still there.
There's still a dead end effect.
Yeah, but I mean it's pretty obvious it's there because if someone says I've got great wind there and I've got enough transmission capacity there, I need to meet that target, take it all from there. But the flows in that will congest certain lines, and then if you put another wind farm somewhere else, you end up with transmission congestion. So I think the insight is obvious, but with curtailment, allowing curtailment, the answer is not as crisp or clear because I can curtail it.
And presumably you can put a cost on that suboptimal route. If the route you take is we'll optimize for 5%, then we'll optimize for 10%, 15, 20. You can cap the cost of that suboptimality by saying, at worst we will dig up the wind farms here and we'll put them somewhere else. You actually have a cost that you can associate with that suboptimality. And thinking about David's question about there'll be an optimal solution that involves the market versus one that involves central planning. The central planning one will be suboptimal, but maybe we can look at how much the suboptimality in different routes will cost us.
Some of these results are so intricate and detailed. I don't think any market could deliver them. It'd be too difficult. So what are you going to do? Design a market that takes into account the fact that as the transmission system builds out, the optimality of it changes. I wonder how you're going to put that into a market. Well, I don't know how to do it. Do you?
Well, you better start thinking.
I mean, some of these, I think some of these issues are so technical and difficult and complex that I mean, put it this way, you just admit this gentleman here in the front row, I'll get your name later so as you can use it. He claims to me the UK market just failed. You don't have an awful lot of wind in the system already and just failed. So, you know.
Well, we're going to have it, if what you're saying is true, at the moment that Ofgem is in fact encouraging generators to site, the cheapest place to be sited was where there's spare capacity.
Yeah.
And what you're saying, if you put something there, later on in 3 years' time, you're blocking something else,
Yes.
and you make the wrong decision.
Yeah, of course.
Hasn't Ofgem sent
But we've always known that. That's not. I'm not telling you something we didn't know before. I mean, Yanis here, we all know that. This just illustrates. Well, I think the other reason we did this is we're trying to show that with lack of transmission, because people won't allow you to build it, that you should think about using what you've got in the best way possible, and there are ways of doing that.
Peter.
When you have an increasing amount of wind generation in Ireland, from going up to 5 gigawatts, and you're going to have wild swings in wind, well, because of wind variability, you're going to have big changes in the amount of wind generation over a period of hours.
Yeah.
You're going to have a corresponding big change in thermal generation.
Yeah.
Is there increased risk of voltage collapse or breakdown of the system?
Not a voltage collapse, but there's a possibility that we will not have enough flexibility in the system, which is what I was trying to get at when I was talking about the flexibility here.
Just be more.
Yeah, that shows the change in 15-minute deltas. So you end up with, you can see here, you're going to have way more 250 minutes, the 250 minutes, 15 minutes. You're going to have much more variability to deal with. But the simulations that we've done on the 2020 Irish system, on the basis of 1 hour resolution with Wilmar, indicate that our plant mix is flexible enough to deal with. It's ironic but true. The Irish system is a small system on an island, therefore people said it's very difficult to integrate wind. The truth of the matter is, because it's an island system, it's always been very flexible because it had to be. And it turns out it's easier for us to integrate wind because it's flexible. So it's a sort of a, it's like the Ethiopians, they learn to run at a height, and therefore when they come down to land, they beat everybody. It's the same thing. We were an island, we were flexible, we always had to be flexible. When the ESB, back in the old days of the ESB as a vertically integrated utility, when they built a power station, they went to Siemens, ABB and whoever, and they spec'd it, and it was an incredibly flexible specification because we're an island. We had to have all the flexibility ourselves. So our system is fundamentally very flexible to start with. Whereas if you go to the United States, on the Eastern Interconnection, an awful lot of their plants are incredibly inflexible. Their coal plants they built 30 years ago, they turned them on then, they won't turn them off for another 20 years. They're just on and off. So the flexibility, we have flexibility, we can deal with it. But flexibility is a very, very important issue. And we've dealt with it on a 1 hour resolution. We're not sure what happens at 15 minutes. That's why we've taken Wilmar and we're now going to start running a 15-minute resolution to see if we're correct. 1 hour resolution is probably not enough.
I just have a point on the flexibility. You mentioned quite a number of times how important it is, and you had your paradigm. How have you gone about sort of developing that to that point of the issues that are important in your flexibility?
I've said this 3 times today. I've said there's certain things I can't tell you. This is another one. There's FERC study I can't tell you about, the TSO study. They're all going to become public domain. There's an IEA, International Energy Agency, they're doing a piece of work on this at the moment. And those results should be out by the end of the year. So they're trying to quantify flexibility. Now we also, in parallel, have also developed a flexibility metric that's based on the same on the same concept as the capacity credit. Capacity credit is a ELCC. It's a calculation to say, do I have enough capacity? We've adapted that and said, do I have enough flexibility? But it's got some problems with it, but also has some computational issues with it, I was mentioning. So we're starting, but it's a very difficult thing to do.
Can we take Melvin first?
What proportion, you've talked about flexibility, and there are 2 issues of control, it's frequency and the voltage.
Mm-hmm.
Where does the demand for flexibility come from most? Is it frequency or is it voltage? My understanding is that it's frequency.
That's a good question. Well, first of all, the area of flexibility that we're working in mainly got to do with megawatts, so it's frequency. But I'd say on the megavar side as well, we're going to need more flexibility essentially as well, aren't we? Yeah. So there is a megavar equivalent as well, but what we're dealing with here is mainly megawatts. But definitely the flex. In fact, at this meeting the other day, I did mention that we should say in this report that we're only dealing with the megawatt issue, that there is a megavar issue that we haven't really dealt with. But it's mainly megawatts. But megavars are important too. Remember, the wind turbines or the wind is very megawatt wise, they're not really very megavar wise. So probably not as big a problem as the megawatt.
So is it the standards that are driving the megavar requirement and the megawatt requirement for flexibility? Is it?
There is none.
There are no standards.
No, not for flexibility. For total amount of capacity there is, but not for flexibility.
But on frequency and voltage there are standards control.
Yeah, I suppose they do. Yeah, but they do drive it for sure. That the system operator knows they've got it. But there's no metrics. There's no in the North American in the NERC in the US. There's no metrics that system operators have to obey with regard to flexibility. They have to have certain capacity adequacy metrics, but they don't have flexibility metrics.
Mark, you asked the question about what's the amount of transmission to serve a given wind farm or wind farms. And there is certainly not 100%, and there is not the capacity factor. In this country, the value which was chosen by National Grid is 60%. So what?
That's the value National Grid would like to choose.
Okay, so. And it was based, well, there's still discussion going on whether the 60% is right or wrong. So have you got any idea what's the value in Ireland and what's the appropriate value?
Well, that's what we're trying to do. We're trying to run the same. We're trying to run this analysis is limited. We mentioned this before. It's got various assumptions in it that are not really, real. We're trying to run the same analysis now to try and see how much is the optimum amount of transmission to build. A trade-off between building more transmission and curtailing. But that's what you're going to have to do. Look, we will curtail wind. It's one of the facts of life. And it's a good thing that you curtail wind. It means that you haven't probably overbuilt your transmission system.
Is there anything in the grid code at the moment, or planning guidelines or whatever? What's the optimal amount of transmission capacity to serve wind?
No.
Can I just make a comment? It follows on from something Mark said earlier and what Janusz just said about 60%. That there are the two approaches to how you might solve this planning problem. One is basically what Mark is doing, where you do a cost-benefit analysis between the cost of constructing additional transmission and the cost of curtailing wind generation. The alternative is to come up with some sort of deterministic heuristic rule. And deterministic heuristic rules are, I think it's fair to say, primarily based on annual peak, on just looking at the time of annual peak demand. And the fundamental difficulty with that is that just looking at the time of annual peak demand doesn't reflect the true nature of this wind integration problem, which is that you're looking at the costs of constraining wind year round.
Yeah, well, that's my point about having 3 planning periods as opposed to the whole year round.
Yeah. In GB, the proposal would be just to use not 3, just 1.
1.
Yeah. My comment was that in order to use just 1 planning time for the wind integration part, you would need a very, very good justification.
For which they answered?
I haven't seen one yet. That was off the record.
This has been taped apparently. I just signed a. Did you sign one of these?
I forgot that. I think they
trying to dig himself out of a hole.
My one saving grace is that the people proposing this do know already that I'm a bit sceptical.
Can you say something about the feasibility of storage in Ireland?
Oh, absolutely. My favourite topic. How do you mean by feasibility now?
On what sort of scales might it be feasible over?
Yeah, well, we've done that, and I have the slides in there, but I won't call up. We reckon that to build mass storage, you're talking about compressed air energy storage or pumped hydro, that you need penetration levels of around about 50% energy. Because at 50% energy, you're dumping a lot of wind, and that is nominally free. Now, I'm not saying that you should go to 50% because the incremental cost of energy at that point is huge because you are dumping so much wind. So if you were told you had to go to 70%, then I think building storage is vital, but not until then. And the main reason it isn't is because it's very expensive capital-wise, and every time you put a megawatt in, you don't get it back out. And it's a very simple calculation that can be done on the back of a business card, but yet people keep on time and time coming back with it. Storage is not a technology that is feasible economically until very large penetrations of renewables. And in Ireland, the penetration level looks like about 50%.
Any more questions? Particularly, I'm a bit conscious I've been looking at the front of the room, so go on.
Yeah, I don't know Ireland, so maybe would you have any storage capacity with hydro?
Yeah, we have.
Which makes sense. I mean, even with less than 50%.
We have hydro around about 300 megawatts of hydro, but it's very restricted because of the levels in the lake. So hydro, believe it or not, in large cases is not that flexible. In theory it's flexible, but in practice for environmental reasons it's generally not that flexible. We have 300 megawatts on rivers, and we have one pump storage station. But even when we take out the pump storage station, we still, from the point of view of wind and curtailing it and saving the energy and all that good stuff, you still wouldn't build it. We do have pump storage for technical reasons, have to do with reserve and things like that, which we do need. But once we have one of those units, then we have all those ancillary services issues dealt with. We don't need another one.
Any further questions? I think we're 20 minutes past schedule, so we ought to be winding up pretty soon. Any more quick questions? One more.
Just how the CO2 emissions are coming into the play for the Ireland, for example, for your mix of the generation? Because in order to support your wind, you have to have the reserve. So where is it coming from?
Where is what coming from?
The generation for the reserve. So is it coming from the coal, or how much do you really hurt the CO2 reduction? Which you
there was a comment made yesterday by someone that the carbon clawback because of this issue is around 1 to 7%. Isn't that right? Someone said that.
That was the UK grid, though.
Yeah.
For the British grid, rather.
Yeah.
Sorry.
Yeah. I mean, the simple fact of the matter is that if you do the carbon calculations on this, largely speaking, you do get carbon reduction. It's pretty dramatic. And as you go higher penetrations, it starts to saturate a tiny bit, but not dramatically. It's interesting though, if we get to our targets, and depending on what happens in the UK, on the models we've used, we'll reduce our carbon by 25%. We'll reduce your carbon in absolute terms by 80% of our reduction. We'll have almost a bigger impact on you, because when it's windy in Ireland and we are exporting to you, now it all depends on what you assume is going on in the UK, so I'll accept there's all sorts of, but in the results that we got in the All-Ireland Grid study, we'll be displacing your coal, but we'll be displacing our gas, and you get twice as much bang for your buck. It turns out we'll reduce your carbon almost as much as our own. So that's the classic case of this. Once you've interconnected systems, and transmission lines, you end up in a situation where your wind reduces someone else's carbon. That happens a lot in Denmark at the moment as well. But that's based on a set of assumptions that may not be correct.
Okay, so should we thank Mark again? He'll be around over lunch.